let us move on to the proof of this proposition. So the first observation, and this is a very keen and slick observation, is we're assuming that these random variables are not integrable. And because they're not integrable, we can even multiply them by a small number or divide them by a large number, which is the same thing. And this is still not integrable. And now we're going to notice the following. We want to understand this event, that is when xn is larger than n times k. And we want to sum these probabilities. At this point, we are very used to the idea, why do we care about summing probabilities? Well, that's because we can use Borel-Cantelli. And that means, but now we're going to use the fact that they're identically distributed. And being identically distributed means that we can replace n by 1. And why do we bother doing this? Because now if we focus only on what is written here, we have a theorem from previous unit when we were studying integrals, and this, this is finite if and only if x1 over k is integrable. Yes? But since it is not integrable, we can conclude then that it's infinite. And then what we have this sum is infinite, indexed by only the first random variable. This sum is infinite. Why? Because the first this random variable here is not integrable. But now when we go back here and use the fact that they are identically distributed, now we have a sequence of events, each one indexed by a different random variables, and this series, it diverges. And because it diverges, we can use Borel-Cantelli lemma 2. So here's when we use that they have the same distribution, and here is where we use that they are independent and identically let us go back here in this proposition. Indeed, we assume that they are independent and identically distributed. So we can conclude that xn will be larger than k times n for infinitely many values of n, with probability 1, almost surely. And there is a number k here. Now we can take the union over k, and what we get, just rewriting what is here, is that this event here, its probability is 1. What is the event? Is the event that for every k, xn will be larger than k times n for infinitely many values of n. So this is for each k fixed. You fix k, there will be infinitely many numbers n for which this inequality here will hold. And of course, as we increase k, we need to look farther and farther away to find these numbers n. So from each k, you may need to look very far to find such n, but it doesn't matter. What Borel-Cantelli lemma is telling us is just look far enough and you will find it. We find this event, it has to occur infinitely often. So with probability 1, our sequence of random variables satisfies this property. And to conclude the proof, what we're going to show, and now it has no probability involved anymore, is for each sequence of numbers, deterministic sequence of numbers, so see this is a lowercase x, if they satisfy this condition here, then when we compute the sum, the partial sums of these numbers, when you compute the partial sums of these numbers and divide by n, so we're taking the average of the first n of these numbers, we're going to prove that the lim sup of this sequence is plus infinity, and therefore this sequence cannot converge to any real number. So now what is left is to prove the claim in this paragraph here, and this is what we do in the next slide. So what we have to show is that for every natural number r, natural is enough for our purposes, we can find some number m for which this average here is larger than r. If we can do that for every r, we are constructing a subsequence of m's that tends to infinity, and that's exactly what it means for the lim sup of a sequence to be infinite. So this is what we have to show. We have to show existence of m such that a certain inequality is satisfied. So let us show existence of such m. We suppose xn satisfies that condition. Let us go back here. Suppose the sequence xn satisfies this property. And what we do is take k to be 2 times r. This is the r that was given to us. And take n such that xn is larger than k times n. This is exactly, let us go back here, this is exactly when we are using this assumption here. And now there are two cases. The first case is when Sn minus 1 divided by n minus 1 is already larger than r. In this case, we just take m to be n minus 1, because this is exactly what we had to show. So this case is solved by taking m with this form. And now we need to consider the complementary case. So let us assume this is less than r. In this case, we're going to show that Sm over m will be larger than r. And to do that, we just do the estimate backwards. We use this combined with this. Remember k, we're taking k to be 2 times r to get what we want. And how do we do that? Well, right, what is Sn over n? It is just this. This is what we're trying to show. So what is Sn over n? We're writing it here. And now we are splitting the sum, taking out the last term from the sum. And when we take out the last term of the sum, so this sum here is bounded from below by the difference between the absolute value of xn and the absolute value of the sum of the previous terms. This is just the triangle inequality written backwards. So this is just an exercise of how you manipulate absolute value to get this inequality. And now we're going to put the minus 1 here in front. So we get again a lower bound, because the numerator and denominator are both non-negative. I'm decreasing the denominator, so this is a lower bound. So what this fraction here with n minus 1 instead of n gives is actually an upper bound for the second term here, but with the minus in front of it, then what we get is a lower bound. And now here at this point, we use the assumption that this term is at most r, so it's bounded from above by r, but there's a minus in front of it, so it will be bounded by below, from below by minus r. And now we use the other assumption, which is that xn is larger than k times n, and k equals 2r. So this is k is larger than k times n, but k is exactly equal to 2r. So this is r, and this concludes the proof and concludes the second part of this video lecture.